In this video, we are going to talk about velocity distribution in an open channel. So far in all our calculations, we had assumed average velocity, which is denoted by V, which is supposedly constant over the entire cross-section for any given cross-section. Now, what happens in reality is when we have an open channel, particularly one where the B by Y, the bottom width divided by the area. So when B by Y naught, which is the uniform flow depth or the normal depth, is large, flow is two-dimensional. And hence the velocity distribution over a channel cross-section is usually not uniform. In fact, for a trapezoidal channel, the energy correction factor alpha is 1.1, while the momentum correction factor beta is 1.05. Neither of them is exactly equal to 1. If you recall from our earlier discussion, so this is our energy correction factor, which we would have used for calculation of the Froude number, and we had also looked at momentum correction factor. For example, in hydraulic jump. So here is the momentum correction factor. So we had assumed this to be 1, as well as the energy correction factor also we had assumed to be 1. However, in reality that's not the case because the velocity distribution is not uniform. In fact, if we look at how the velocity distribution would look in reality, if we have the channel bed given by the bottom axis, and if y denotes the depth of flow starting from the bed, then the velocity profile is not linear, as we can see. The maximum happens not exactly at the surface but slightly below it. So this is where the maximum happens in reality, and at any given depth the velocity u, so u is a function of the depth y. So this is what happens, and this is for fully developed. Similar to the concept of fully developed flow in pipe flow, this is fully developed flow in open channels. So if we have a fully developed two-dimensional open channel flow, here the velocity distribution is given by the same law, which is the logarithmic law, which is valid for turbulent flow in pipes. So Prandtl's logarithmic velocity distribution, which is valid for pipe flow, turbulent flow through pipes, is also valid in case of open channels. And if we assume that this maximum velocity happens right at the surface, then the velocity defect law, which comes from Prandtl's logarithmic velocity distribution, can be used to obtain a relationship between u, the velocity at any depth, to the depth, corresponding depth y. And here u star, as we had noted earlier, here in case of Chezy's equation, so u star here is the shear velocity, and so u star, the shear velocity, is given by shear stress divided by the density. Shear stress is already, we have an expression for the shear stress, so when we plug that in, the u star shear velocity is given by square root of gr s naught, and that same u star also appears in the velocity defect law. So here u star is the shear velocity. So for y by y naught greater than 0.5, which means slightly away from the boundary when the depth is larger than 0.15 times the total depth, for that region the velocity defect law holds, which we can see is a logarithmic velocity distribution where this term kappa is Kármán constant, whose value is roughly 0.41 for open channels. And if we convert this natural logarithm to the base 10, then the final expression for the velocity defect law is given by this expression. Now remember, we are interested in the average velocity over the cross section. Over the channel cross section. So we would want to get the expression in terms of the average velocity also, and the average velocity can be obtained by integrating this equation for any generic velocity at a depth y. We integrate it over the entire depth to get the average velocity, and when we do this and we rearrange the terms, we get the velocity defect law in terms of the average velocity. So v here is the average velocity. Um in the previous expression was the maximum velocity. And we had assumed it occurs at the surface, however in reality it occurs slightly below it. So we can use this velocity defect law to get the distance, the depth y, from the bed at which this velocity u would be exactly equal to the average velocity. So this depth at which u equal to v, so the left hand side is 0, which I write here, and when we solve we get a relationship between y and y naught. So when we are looking at the velocity which is at a depth of 0.367 times the total depth from the bed, then that velocity is exactly equal to the average velocity v. Now what happens in reality is when we measure velocity in open channels, an anemometer is a typical instrument. You can see there's a propeller fixed at the end of it. So this sort of anemometer, also called velocimeters, these are used to measure the velocity of flow in open channels. What happens is these anemometers have to be inserted from the top. So it's the depth from the top that we are interested in and not from the bottom. So from the top surface at a depth of 0.63 times y naught, the velocity that we measure at this depth, 0.63 times y naught, this velocity would be equal to the average velocity v. So if we are to measure the average velocity at any channel cross section, we are to insert this anemometer to a depth of 0.63 times the total depth. And similar to pipe flows, we also have the law of the wall here. So this shows us that although for all practical purposes we had assumed the velocity at any given cross section to be a constant value v, the distribution is actually not uniform. At any given depth y, we do have a velocity which is a function of that very depth. So in the next video we will discuss about how to use all these concepts that we have learned so far in open channel flows to design channel sections. So see you.